Catch slow LLM calls before they cost you users. By the end, you will log every LLM call with a clear schema, detect when responses exceed your latency budget, and see a rolling view of slow calls and error trends. You will learn how to turn raw timings and token counts into actionable alerts and dashboards. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. Monitoring and logging matter because they optimize reliability and user experience. Latency is the main metric here, the time from request to response. You trade latency against richer responses and cost. At scale, a 10% drop in response time can cut cost or raise throughput. Good logs let you spot regressions, tune timeouts, and justify model choices. The intuition is simple. Capture structured events for each call. Check timings against a budget. Rank and smooth noisy measurements. Finally, summarize errors and token spend. This shines when you run many short calls and need fast feedback. It falls short for one-off experiments where human review beats metrics. We will build a small monitoring pipeline for a customer support prompt corpus that records each call, enforces a latency budget, identifies the slowest calls, smooths measures over time, and reports error and token cost summaries. Now we will show how to capture a single structured log for each LLM call. This snippet shows how a single LLM call becomes a structured JSON log with fields like timestamp, prompt ID, latency in milliseconds, token count, response status, and any error message. It writes one clean record per call, so downstream tooling can parse and filter reliably. The idea is to separate metadata from raw text so you can query by prompt ID or status. If you increase the metadata you log, storage grows, but troubleshooting gets faster. If you log less, you save space but lose signal for diagnosing regressions. Next, we will check each call against a latency budget and report the result. This snippet enforces a latency budget check by comparing the measured latency to a budget threshold and recording a pass or fail flag with the call. It also emits a small event when the budget is missed, including how much over budget the call was. That lets automated alerting and dashboards count misses. If you tighten the budget, you'll see more failures and more alerts, which can push you to optimize prompts or switch models. If you relax it, false alarms drop, but user experience may suffer. This is the place to tune trade-offs. Next, we will rank recent calls by latency and pick out the slowest ones for inspection. This snippet sorts a recent window of call logs by latency and selects the slowest 2 entries for quick review. The output highlights prompt IDs, latency, token counts, and error states, so you can see patterns like a particular prompt that consistently runs slow. Choosing 2 slowest is an adjustable parameter. A larger number surfaces more problems, but requires more human attention. Smaller selection gives a sharper signal for engineers. This ranking helps you prioritize which prompts to optimize or which responses to cache. Next, we will smooth latency readings with a sliding window average to reduce noise. This snippet computes a sliding window average over recent latencies to smooth spikes and show trend more clearly. The window size is the key parameter. A longer window makes the curve stable, but delays signal for new regressions. A shorter window reacts quickly but shows more variability. The smoothing helps you avoid chasing single outliers and instead focus on persistent shifts. It is useful on dashboards and for threshold detection when you want fewer false positives while still catching sustained slowdowns. Next, we will summarize recent error rates and token cost to track reliability and spend. This snippet aggregates recent calls to produce a small summary of error rate, average tokens per call, and total token cost for the period. Error rate is the fraction of calls with non-successful status, and token cost is the sum of tokens multiplied by per token price, both useful for operational decisions. You might slide the summary window to daily or hourly depending on traffic. Increasing the window smooths variability, but can hide short bursts of failures or cost spikes. This summary drives budget decisions and incident postmortems. Recap! What we built: a per-call JSON schema, budget checks, slowest call ranking, smooth latency trends, and an error plus cost summary. When to use it: production systems with many short LLM calls where latency and cost matter. One caveat: aggregated metrics can hide fast transient issues, so keep raw logs for deep forensics. Next step: scale this pipeline by adding an approximate nearest neighbor index for prompt templates, or by increasing the sliding window size and adding timing percentiles, so you can evaluate tail latency and cost under heavier load. If practical AI engineering helps you ship reliable LLM systems, subscribe and watch the AI engineering videos.